5 in this machine learning operations course. Here we would focus a little more deeply into the model development lifecycle. So far, we have actually looked at ways in which versions of data, versions of code, and versions of models can be tracked using options like GitHub Actions with CML tooling on top of it. And prior to that, uh, feature changes using feature stores like Feast, as well as data changes either in the database using concepts like SCD type 2 or with flat files where DBC plays a critical role. So in this lecture, we will dive deeper into how model versions can be tracked, various options for optimization runs are, how are they tracked, as well as the entire development lifecycle to be able to have control on what gets developed and what gets promoted to production. With this, we would actually be completing the CI part of the CI/CD as it pertains to ML. And then in subsequent lectures, we would focus on the CD part of it, which is the deployment part of it. So for model development itself, we obviously know about various types of libraries like scikit-learn, PyTorch, TensorFlow, etc., etc. So the goal of this week's lecture is not to go into details of how to develop using any of these libraries, but more to motivate the need for tracking the development lifecycle and then looking at the tooling that exists around how we can make this better than the typical run-of-the-mill brute force approach that we all tend to follow. Now, the thing with model development is that it's not just code at the end of the day. Obviously, code gets tracked using GitHub or Git-based deployment platforms, but we're talking about more than just code. So, what what are the different types of behaviors that we see when we develop models by ourselves, right? One is the fact that we have to tweak parameters pertaining to the model selection, and when that happens, we sometimes do not keep track of the parameters and the changes they've gone through. When we first build a model, typically we end up hard coding the parameters inside the code. So that by itself is not a problem because code versions get tracked through Git, and therefore any parameter changes that happen in the code also get tracked through Git. But the moment we start to modularize the code and make parameters as a configurable file, and then that file sits separately from the code, then things start to get a bit problematic because the changes to the config file might or might not be tracked because you might not have added that to the GitHub or Git repo. So tracking of hyperparameters is a critical step, and unless we track it, the ability for somebody else to reproduce the model and its efficacy becomes a challenge. The second aspect of the behaviors that are typically there in model development is um, notebook style development. And there is a whole plethora of problems that emanates from the use of notebooks for the purposes of governance and observability and things like that. While it makes the development easier, it makes the aspect of tracking the development a little harder. One example would be matrices that you plot with respect to accuracy, with respect to coverage. So it's quite easy for you to plot, let's say, an F1 curve or to track the accuracy loss comparisons as the epochs go on for a deep learning neural network training. But then the moment you make some changes, let's say, for instance, you're not happy with the accuracy, you come back and change the model layers, and then you do a training run again, the matrices end up getting overwritten because the same cell in the notebook gets executed. And when this happens, you no longer have track of what are all the changes that you have made and the corresponding impact on the output matrices. So this becomes a big issue when especially you've got to collaborate with other data scientists or machine learning engineers or the business to convince them that these changes in the model are worth doing. The third angle of behavioral problems that exist when it comes to model development is unversioned models. Actually, we saw this in the motivation case for CI, right? What we've noticed is that when you end up doing model development on your own, and let's say you promote versions of models, then which version of model got taken up by what output mechanisms or what pipelines is something that is typically not tracked, because models themselves as an artifact are not part of Git in many standard repositories. So that's a problem. Manual deployment is a huge issue. We tend to do that as developers, but then obviously it's frowned upon when it comes to enterprises. Therefore, we want to try to avoid that. Deployment is just a natural consequence of development, right? And as standalone data science operators, we tend to do all of it ourselves. But in an enterprise, that's absolutely not done. And last but not the least is the environment that encapsulates what is required for a model to run. Typically, this is more than just the code. It obviously includes the virtual environment that you might create using Python, but also the libraries, the packages, and the dependencies. And unless you package all of that correctly, you're going to have problems with respect to reproducing these results in some other machine. So that goes to this classic syndrome of, hey, it worked on my machine, what about yours? So these are the reasons why model development itself as a life cycle needs to be tracked beyond, over and above what typical code tracking happens using Git. So let's just take a step back and look at the uh, artifacts that gets produced using the model development lifecycle. First and foremost, the execution environment itself is a critical variable. Like we just spoke about, the environment comprises of operating system, the libraries, the dependencies, and things like that. Configurations also play a role in the environment. Now, within the environment, obviously, you're going to have artifacts pertaining to the code, which specifies what the pipelines are, the data processing steps are, the data, because that influences the model outcomes, and the model itself. All three are artifacts sitting within the environment. Now, the environment itself can change based on where the model development happens. So, if you look at a typical workflow in an enterprise, you're not going to be able to have access to production data. In fact, in most enterprise settings, or even medium company sizes or small company sizes, you're going to have to do development in a separate environment, which has absolutely no connection or very little shared infrastructure or resources with the production environment. Obviously, the reasons are privacy or security related, because if you do something wrong in the development stage, you don't want that creating an impact on the production infrastructure. So, at the minimum, the common scenario you're going to face in the real world is a separation between development and production. When it comes to machine learning, especially at large scale, and even, for instance, working on generative AI kind of use cases, you're going to have a third environment, which, for the purposes of our discussion, we're going to call it staging, which sits in between the development environment and the production environment. In the staging layer, we're going to have the ability to run the developed models from the development environment against larger data sets which are real. And when it runs against larger data sets that are real, it provides the real world validation that we need that the model is actually functioning fine. So, what do we mean by that? In a typical machine learning development lifecycle, the development environment is where the model development happens. And when model development happens, you're going to operate on samples of data, let's say 10 rows or 100 rows, which has the same schema, which has the same, hopefully, underlying distribution of the data, as well as the rest of the pipelines that are required to consume the model output. So all of that gets uh, instantiated or developed for the first time in the development environment, and it gets unit tested as part of CI/CD processes, and then it reaches the developed stage. So the artifacts that we spoke about, which is code, the models, and the data, are all pertaining to the development environment. And once its gates are passed, the uh, artifacts reach a developed stage. At this stage, you might still not have the confidence that this would work in production. because the volume of data in production is going to be much, much larger. The velocity of the data is also going to be different. And thirdly, the data types or the values which some of the rows of the data might have in the real world might be different from what is conventionally expected. So what ends up happening in most scenarios is there is a staging area or a staging environment where these developed models get deployed, and they get tested against more rigorous methods or mechanisms, using more rigorous mechanisms. So one such example would be the data set that's there in staging will be almost like what's there in production, but without the sensitive information like PII data, like personally identifiable information. So in that scenario, the staging environment becomes the closest proxy you've got for production data, and you need to execute the artifacts through the staging environment in order to gain confidence that this works at production scale with production like data. And in case the tests fail, either because you're not anticipating some behavioral changes in the data that happened in real world. Obviously, these didn't get modeled in the samples in development environment, but the staging environment testing caught it because the data set there had these small variances. So in which case, you've got to go back to the development environment, fix your pipeline, make it more robust to data quality issues, etc. Or the underlying distribution of the data is actually significantly different from the samples that you've worked with in the development area. And that could be a problem for the model that you chose because the model assumed certain properties about the underlying data. So various scenarios possible, but staging as an environment is where the validation against real world data happens. And once that's done, then it gets deployed into production. In production is when it's deemed to be deployed, which means it's the final version that's running live. So this distinction is something that is going to play a crucial role as you go through the development lifecycle and you adopt the best practices that we will be talking about. So there are two lifecycle patterns that are important to keep in mind. These patterns are going to guide you as you work through model development and cycle through these environments. So for ease of representation, we're going to call the development environment as dev, the staging environment as staging, and the production environment as prod. So the classical approach that we want to follow is to do the bulk of our development, in fact, all of our development in dev, and then uh, be able to have model outputs validated in staging against real world or close to real world data, and then finally deployed in production for live usage by the company, by the enterprise. So the training code itself is depicted using this icon, and then the model is depicted using this half brain icon. So the first lifecycle pattern that we will see is something called as deploy code. As the name suggests, the common activity that gets done across all of these environments is the act of deploying code into that environment and then having the code that's deployed execute within that environment. So what this means is, in a typical development lifecycle, the dev stage or the dev environment will have the code be developed against samples. It produces models, and the models get tested in a unit test kind of a manner and simple functional tests to prove that the code is fine, the model works as expected. But naturally, at this stage in devs, there isn't any real world data to speak of that can give us the confidence that this can be moved to production. So what you then do is you take the code that has been tested and move that to the staging environment, or make a copy of that to the staging environment, and then run that code again to train a brand new model, right? A brand new version of the model in staging. The reason I'm saying it's a brand new version of the model is the data that's accessible in staging is different from the data that's accessible in dev. Dev was just samples, whereas in staging, you're going to have close to the real world production data, maybe 1/5 or 1/10 of the production data without PII information, etc. So with that closer to the real world data, the code, which is the same as what you developed, gets run against it. And the model that's now produced is obviously going to be different from the model that you trained with sample data. So these two half brains that you see are actually different. And this model is again tested through unit tests, through the CI part of the integration, what we saw in last week's lectures, right? Again, it's tested for accuracy, various output matrices that you might have. And then there is an assessment made that the model is good to go, or the model has errors, or the model needs more work, etc. At this stage, what we have only done is copy the code over and trained it afresh on real world or close to real world data. Okay, let's say that the validation turns out to be successful, and even on the close to real world data, the model is proven to be useful, and now we are confident that this will work in production. So at this stage, what happens is the same code gets copied over to prod, and now production data is the one that's actually getting input to the code. The training happens on top of the production data to produce the production model, and that model becomes the final model that goes live. Naturally, when production data comes into picture, there isn't any human involvement that is expected, because we wouldn't want the typical human in the enterprise to come and access the production data due to data privacy security issues. So we are expecting that the entire training process is fully automated, provided the data set is configurable, right? So the input data should be configurable. Everything else, which means the environment of the execution, the training steps, the production of the output artifacts, which is the model as well as the associated matrices for accuracy, loss, etc., all of that is automated. All of that is done without any human involvement. That's the expectation for this kind of a lifecycle pattern to work. So in essence, the code is what's getting moved forward to the environments. The model is not. The counter lifecycle pattern that's possible is deploy models as opposed to code. As you can expect from the name, what is getting pushed forward or promoted to the next stages or next environments is the model that's actually getting produced at the first step. So here, the development stage itself has produced a model which is actually worthy of being tested at larger scale with bigger data or with production grade data. So therefore, the model gets copied over to staging. In staging, there is a bunch of validations and tests that are done, and then once that's satisfactory, that model gets copied over to production to then be used for deployments in various pipelines for model serving, for inferencing. So here there is no training that actually happens in staging, no training that happens in production. The training all has happened in dev, right? So that's a big difference compared to the deploy code lifecycle pattern. By the way, both of these graphics have been taken from the databricks.com website. Databricks is the vendor that has the majority contributor privileges to Spark, as well as they are the creators of very useful open source tooling around model development, model lifecycle management, etc. One of which we will use today in this week's lecture, which is called ML Flow. Anyway, coming back, so we see two distinct patterns of how the models can be developed and deployed. So let's compare the two. So in the deploy code lifecycle pattern, the main artifact that's getting produced or that's getting certified or validated is code. Whereas in the deploy model lifecycle pattern, it's the model that's actually primary. Model training happens in each of the environments in deploy code, which means every environment needs to have the associated ability to run the code, which means it needs to have dependencies mapped out, the package is installed, configurations worked out correctly, etc., etc. Right? So keep that in mind. Whereas in the deploy model lifecycle pattern, the model training happens only in dev. So then what's required for subsequent stages to work is only for the model to be executable, not for the training runs to happen, which has a crucial implication, which is that what about access to production data or production like data? In the deploy model lifecycle pattern, we would need access to that data in dev. Unless we have access to the data, the model that we produce in dev, we will never be able to have confidence that that model is actually going to work in production as well. Imagine if you trained only on samples and the model that you produced, you make a erroneous assumption that this is going to work in production, and you copy the model and put it into production. While it might produce some data or output, very likely those are wrong because it's been trained on much different smaller data sets than what is it in real life, right? So production data access or production like data access is necessary in dev environment itself in order for deploy model lifecycle pattern to work, which has a huge implication on security, right? So therefore, if you are going to go about choosing deploy model as a lifecycle pattern that you want to follow, you better make it amply clear to your stakeholders, your IT teams, that production like data access is something that's going to be mandatory for your work to happen. Or put it in other words, you might not be able to choose the deploy model lifecycle pattern in many enterprises because production data access is not going to be available. Whereas in the deploy code lifecycle pattern, the production data access is only required in production, not even in staging, right? So the separation of environments is clean. The benchmarking of models refers to the fact that if you've got a challenger model that you're building right now, you've got a champion that's already live in production, then to be able to compare the two for accuracy comparisons, for efficacy comparisons, etc. In the deploy code lifecycle pattern, this happens in production because you've got a new model there that's getting trained, and then that model gets deployed as a challenger model. The existing champion model is also deployed in production, so you can compare that together. Whereas in the deploy model pattern, you're going to have to make a decision on moving forward with the model in the dev stage itself, having trained it on production data or production like data, which means the benchmarking that you're doing will have to happen in dev, right? So think about what that means. You would need access to the champion production model in dev in order for that benchmarking to happen successfully. Note that you could argue that I don't require access to production champion model, and I move forward with just the challenger model itself as its outputs get produced and I record it, and then I only do the benchmarking in production. But then by that time, the feedback from that benchmarking might not be timely enough, right? And then you'll have to repeat the entire cycle if that feedback turned out to be grossly negative. So at least the first few iterations again of comparison with the production champion model might be required to have happened in dev stage itself for the developer to be able to take some action that's meaningful. So that's a critical aspect of model benchmarking. So this might cut short your iteration time because you've got now access to production data in dev, you've got access to production champion model also in dev. So you can iterate faster, you can move faster, create a challenger model much faster. But it has challenges with respect to the security of providing access to both the production like data as well as the production champion model. So that that has to be balanced out. Finally, the inferencing code that you write in order to use the model that's getting deployed. So for instance, let's say that you've got the iris classification model that we are continuing as the homework model for everybody. Now that model has been trained and it's been, let's say for instance, you've chosen the decision tree as the model that's been selected as the best model that's performing with the highest accuracy. Now in order to use that model, you've got to write code to pass the input data that you get, input iris file or sample that you want to classify now. That has then to be processed in a certain way so that it can be fed into the champion model, the decision tree model. And then the decision tree model produces the output. The output gets processed or interpreted. So all of that becomes part of the inferencing code. That inferencing code is just standard code, right? It's just standard Python, logic. Now, when in the deploy code lifecycle pattern, it's part and parcel of the code. So nothing special about it. It's part of the main artifact that's getting produced or certified. Whereas in the deploy model lifecycle pattern, the inferencing code will need to be run in production, right? Otherwise, you won't be able to use the model, which means that portion of the code cannot be part of the model itself. It's separate from the model, and therefore it follows the standard deploy code kind of lifecycle pattern, which is basically you test that inferencing code in dev, you're happy with the tests, then you move that to staging, and at staging you've basically simulated with production like velocity, production like inferencing, and then you're happy with that, and then that code gets moved to the production, and in production the model gets deployed using deploy model lifecycle pattern, but the inferencing code is basically code that's running in production, which means the deploy code lifecycle pattern gets deployed there, or rather gets used there. So in a sense, even with the deploy model lifecycle pattern, you're going to follow some bit of deploy code for specific reasons, especially related to the inferencing logic. So in a nutshell, the recommendation that most practitioners follow or have for data scientists is to follow the deploy code mechanism or lifecycle pattern for getting ML into production. But having said that, there are a couple of scenarios, or there are specific scenarios in which the deploy model lifecycle pattern might be the best or might work the best. One is when the training itself, model training itself, is expensive. So here's an example, right, of where it is expensive. Think about what was required for ChatGPT to get created, or GPT itself, the base transformer models to get created. If you've read the literature, you know that it was trained on like hundreds of billions of tokens, and these were gleaned from various public corpus or corpus of data, and the ability to run that kind of a training cycle is fundamentally contingent on the availability of expensive GPU hardware. So even with newer age models like DeepSeek, the GPU model infrastructure, the GPU infrastructure required for the model training, it was still there. But I mean, that was still a requirement. They might not have required the latest and the greatest of the GPUs, but the fact remains that training fundamentally in that kind of a GPT-based architecture is very expensive, both resource-wise as well as computationally, and with respect to the amount of data that's required to be crunched through. Imagine now if you follow a deploy code kind of a lifecycle pattern, then you're going to produce a heavyweight model, potentially hundreds of gigabytes in size, and then you're going to certify that, and then again do the same exercise in staging. It's a waste of time, it's a waste of money. What's even more the case is that the GPT class of models fundamentally are contingent on being good performing only when they have access to the complete data, which means in dev stage itself, you're going to give it all of the data that you have access to. So it's production like data available in dev. Any which way you're going to have to train on that kind of a scale of data. So then to be able to have a staging environment, just to have the same data be used for training again is a waste, right? It's redundant. Likewise, the model that you produce as a result of the dev stage activity is capable enough to handle any other public data sets which are commensurate in size, or which are derivative, or which are part and parcel of this universe. So there is no benefit in having a separate production training run. So in this kind of a scenario, the deploy model lifecycle pattern works perfectly fine, right? The crucial assumption here is access to the data that's required for the model to work, and the infrastructure, and the fact that the training is expensive is what makes this deploy model lifecycle pattern attractive for generative AI, foundational model training. Okay, so we'll take a pause here, and then I'll meet you on the other side with more details on how to think about the different environments when it comes to model development.